Sometimes in textbooks, they want you to practice certain skills, and they want to make a word problem that would practice those skills, and they think they're trying to do something in real life, but they make a word problem that's so far-fetched that it is not realistic at all. And this is one of those examples. So here, we've got Clara and 3 friends, all born on the same day, because that happens all the time, March 11th. Leslie is 5 years younger than Clara, Mike is 2 years younger than Clara, Thomas is 3 years older than Clara. You have no idea how old they are, but you happen to know that their product of their ages was 61,136 greater than the sum of their ages. Like, how realistic is that? Like, I don't know how old you are, but I know that your age squared minus 65,000 plus 82 is blah, blah, blah. Like, this is a far-fetched question. But what it does do is it practices some very good mathematical skills that hopefully in more realistic problems you could use. So the first thing that this question practices is you have to pick a variable to represent something. And in this case, since everybody's compared to Clara, it makes the most sense to choose your variable for Clara's age. And this is an important skill in any word problem or in any situation that you might run into in real life that you want to use a mathematical model. What are you going to choose for your variable? And then once you've chosen your variable, can you compare everything else to that variable? So now, Leslie is 5 years younger, so her age will be x minus 5. Mike, 2 years younger, he will be x minus 2. And Thomas, 3 years older, he will be x plus 3. Now this next sentence tells us how we can create an equation with this information, and then if you can create an equation with information with just one variable, you can always solve it. So the product of their ages was 61,000 greater than the sum of their ages. So I'm going to start with words here, because often in a question like this, so on one side of my equation I have the product, on the other side of the equation I'm going to have the sum, and then where does that 61,136 go?
Minus on the product side, minus.
So we could, on the product side here, say this is the bigger one. And you might say to yourself, does it make sense that this is the bigger one? The product's going to be bigger than the sum of their ages. So Peter's saying that we could subtract on this side 61,136, or you could add on the other side. Both of those ideas would be fine.
Which do you like?
I probably add more than I subtract just because subtracting causes more math errors, but this is perfectly fine. Now that we've written this out, now we can go in and put our variables. Product of their ages, what does that mean? Take all their ages and multiply them together. So what would that look like? It would look like x times x minus 5 times x minus 2 times x plus 3. We would still have this minus 61136 on this side. And the sum of their ages would be adding them all up. And that's a little bit of mental math. You could add them all up. You have some like terms. Can you see it's going to get 4x? If you add up the numbers, minus 4. So now we have an equation. And there's going to be two different ways that we can solve this equation and on our graphing calculator. So again, it's going to be a graphing calculator question to figure this out. Method number 1. Method number 1 is you take the left side of your equation and type it into y1. You take the right side of your equation and type it into y2. So we'll go to our calculator and do that right now. Clear everything else out. So I'm going to have x times x minus 5 times x minus 2 x plus 3 minus 61,136. That is my left side of the equation, and in y2, I'll type my right side of my equation, 4x minus 4. Now we don't, on the right-hand side, can you see that that's going to graph a line? On the left-hand side, it's going to graph an x to the 4 graph. Okay? I'm going to just hit graph because we had to see what happens. Wonderful. It's looking really good so far. Oh, we have a little bit of a graph there. And we didn't see our first graph at all. Now, in order to solve this, the way that you would solve this when you type in one equation into y1 and one equation in y2, what you're looking for is where the two graphs intersect. And right now on our window, we can't even see one of our graphs, so we have a problem. So we're going to have to play around with our window and play around maybe with our zoom button to see if we can see both of those graphs. Now, one place to start is if you hit your zoom button, there's a bunch of different zoom things that you can use. If you go down all the way to, I believe it is 0.
You just press 0.
I know, but I want to show. 0 says zoom fit. And what zoom fit does is the calculator tries to fit the graph as best as it can on your screen. It doesn't always do a great job, but we're going to try it to see what happens, to see if we can at least see some of our other graphs. Oh, there's our blue graph. It's swooping up like that. Oh, and our red graph it decided to put right at the top. Can you see that on our current screen we still cannot see where they intersect? But can you see that it's going to happen top right somewhere over here? Now you can go to your window and say, I need to go further to the right. How much further to the right do you think I need to go? I'm at 15. If I doubled it, 30, it should be enough, right? According to how the graphs look. Do I need to go this far down? Negative 61,000? Probably not. But would it be nicer to go up a little bit higher? Yes. So I'm going to change my y-min, I don't know, maybe to, I'll start with negative 10,000. And I'll go up to 10,000 just so that it's nice and symmetrical. And this part is just a little bit of logic and trying to figure out what makes sense. Wow, that's really swooping up there. Does my red graph show up? Yes, it does, and they intersect. So at this point, we can see where the red graph crosses the blue graph. And so under your calculate menu, which is second, and then your trace button, number 5 is intersect. On number 5, it says, which is your first curve? And it's automatically on one of the curves. Push enter. Which is your second curve? Push enter again. Where's your guess? Push enter again. And it tells us where they intersect. They happen to intersect when x is 17. How old was Clara and each of her friends that day? So Clara was 17, 12, 15, and 20. So this method of intersecting in your two graphs, it's a very common method to use when you're solving complex equations. Type one equation into y1, the other into y2, and find out where they intersect. The problem with this one is figuring out your window. So another strategy that can be used to solve this question is take the entire thing and make one side equal to 0. So can you see that that would mean, oh, I still have all of this, but now I'd move the 4x over, which means I'd have to subtract 4, and I'd move the 4 over, which means I'd have to add 4. And I know those two are like terms, and you could put them together if you like, or you can leave them separate. Your graphing calculator will figure it out. So if I moved everything over and made it equal to 0, what that means on my graphing calculator is I'm going to type all of that into y1. So I've already got most of it typed in. Just have to arrow over and subtract that 4x and add 4. I'm going to clear this one out now. And what this will do is it will graph an equation, and now if it's equal to 0, what are we looking for? We're looking for an x-intercept. So in this method, if you make it equal to 0, you'll have to find the x-intercept. So we make it equal to 0 and try to find the x-intercept. Well, the nice thing about finding an x-intercept, we've got it graphed in there, is based on this problem, for my window, I might say, well, what would be reasonable ages? Because we're trying to find their age. Maybe I go up to 100. I don't think that they're going to be older than 100. I mean, we already know the answer is 17, but I don't think they're going to be older than 100. So if I go from 0 to 100, and as long as I have my y-min, it might even be your standard window going from 10 to 10. As long as I can see my x-intercept, I'm going to be able to see my answer. So I don't have to use zoom fit. I'm just going to hit graph, and I'm hoping that the graph crosses that x. Oh, there it is. Boom. It crossed it about there. So I can go now second calculate to find an x-intercept. That's number 2, 0. I need something to the left. I'm going to pick 5. Yes, that's to the left. Something to the right. Well, I'm going to pick 50. I know that's overkill. But is my x-intercept in between those two? Yes, it is. So I can push enter, and I find 17 that way as well. So the x-intercept method is nice because at least you know your window for your y values has to show your x-intercept somewhere. The first method is nice because you can just graph both things separately. You don't have to worry about rearranging your equation and maybe making mistakes while you rearrange it. You can just graph one thing in y1, one thing in y2. So we'll see these different methods throughout. Okay, the questions for this one are 7 and 8.